I'm going to talk about a government-funded project called Capri, where the focus is on overcoming the safety and security barriers to autonomous vehicle deployment. There's a number of contributors to this paper, and you'll see those as we go. So these are the topics we're going to talk about. The objectives of the project itself, mainly from both a business and from a technical point of view, and then talk about the simulation environment and how we're trying to prove both safety and security through the simulation environment. When I say prove, I mean adequate enough for regulation, not from a mathematical sense. Okay, so the first statement there is the business case for the project. It's a £4.2 million project. It's about 16, 17 partners involved, and ultimately there's going to be some public trials at the London's Queen Elizabeth Olympic Park. So that's Q1 2020, I think. But obviously there's a lot of work to do before we get there. The business case is the first bullet: to build passenger, regulatory and market trust in autonomous pods. And these are pods, not cars. Autonomous pods is a practical, safe and affordable way to travel. So this is trying to encourage people to use pods, autonomous pods, as a way of getting around, but also as a complete way of travel. You can actually dial up an autonomous pod and call it to you, and it will take you to your destination. And T&VS are running the work group 4, which is a technical one, looking at safety verification, validation and road simulations. And we're not necessarily trying to say the pod is safe. We're trying to develop methodologies which allow us to then go to the regulatory framework to say that, to demonstrate how pods are safe. So it's a methodology about demonstrating how these pods can be demonstrated to be safe from a regulatory point of view. Okay, so this is a key diagram to what we're doing. So I'll spend a little bit of time to talk this through. So the yellow on the left-hand side, safety scenarios, we'll talk about that. That's Loughborough are looking at what they call accidentology, which is basically looking at how accidents happen and trying to identify scenarios that need to be tested from a safety point of view. So the most common ways that cars crash. And there is an issue about there's not much data about how pods crash, and we'll talk about that. The blue one is a security analysis, so that's the types of cybersecurity threat to the autonomous pod. There's two ways that can happen, and I'll talk about those separately. One is from the fleet instructions, which are coming from the cloud, and one is about how the pod interacts with its environment, and that's been done separately by Warwick. Then there's a simulator from AESIN, which allows us to put the pod into an environment with other vehicles and other actors, be they pedestrians, cyclists, or whether they're just the road signs and traffic lights, etc. So the actual road layout and the various furniture that you might have on the road. And in the green is the pod itself, with the software running and driving that pod, and in the middle is what we're doing, which is a test bench. Okay, so that's a key diagram. Hopefully you can retain that in your head for the next 15 minutes, because that's how it all fits together. That's the big picture for the various bits of the jigsaw puzzle, which I'll talk about. Okay, so the first one is Loughborough. We've got quite a lot of slides, and I'm aware of the time, so these slides are going to be available. There's a lot of detail, so I'll try and go through each contribution relatively quickly. As I said, Loughborough are looking at what we call accidentology, where they look at real accidents and the reasons why they happened. Okay, and as you can see there, the drivers making errors, 95%. Cause 95% of collisions. And they look at various parameters, identify various parameters about the crash, and we translate those parameters into what we can do in the simulation. Okay, so the main point to gather from this is that we're actually basing this on real-world evidence base. I'll skip this slide because it is very complicated, and let's go straight to this one. And what it does is from that accidentology, it builds along these various parameters, it builds an envelope around how accidents happen and the types of scenarios you need to investigate to see, to try and demonstrate safety. It may be hard to read. On the left-hand side, it's cars, cyclists, and people. The cars are the blue one. That's the biggest envelope. And the one on the right-hand side is pods. And the difficulty with this is that there is no evidence base for pods, really. The third one on the left-hand side is mobility scooters, not people. So cars, cyclists, mobility scooters, but there's nothing on pods. So to a certain extent, they're anticipating what the pod envelope would look like. And NAFPA do that research, which then effectively informs the types of scenarios that we need to do in our simulation. Okay, so if you're going back to that jigsaw puzzle, this is the Loughborough yellow box feeding into the test bench to say, these are scenarios which you need to cover because these are the scenarios that are likely to cause accidents with a pod. Okay. We then start to look at the security side of things, and this is Warwick University of Warwick, looking at security scenarios. What they do is they take a reference architecture for a CAV system. So in the centre there is the car itself. The biggest box in the centre is the car itself. On the left-hand side, you have some peripherals, such as sensors, etc., etc. So communicating with the car, either through cable or through Wi-Fi. And on the right-hand side, there you've got the driver and the passenger interacting with the car, either through sensors, such as the steering wheel, or through HMI on the dashboard. And across the top, you've got the cloud. You've got vehicle-to-vehicle communications, and you've got communications with road traffic, with traffic signs, etc., etc., or traffic lights. So there you've got communication with devices which can communicate directly with the car. Okay, so they take that as the attack surface, and as you would expect, they do a threat analysis and try to identify all the specific threats from that surface. And from that, what we're trying to do then is derive test scenarios which allow us to do 3 levels of testing. First of all, there's a theoretical analysis, but once we've done that, then in our simulation, we'll try to run those threats in our simulation and also in a real-world trial. Now, it's important that we do these real-world trials, and as I mentioned, the final one is Q1 2020 at the Olympic Park. But there's 3 trials that build up to that. We've done one trial on Filton Airport, which is a disused airport, but it's a big space, allows us to, and it was just a pod running in a straight line with a dummy passenger running out in front of it. The next one is a big shopping centre, which is taking people from their cars to the shopping centre in a pod. And then say we culminate with this real-world trial at the Queen Elizabeth Olympic Park. The idea is that the data from those real-world trials will allow us to validate what we're doing in simulation to make sure that the simulations we do reflect what goes on in reality. And so the data that we pick up from those trials are put into the simulator as well to make sure that the 2 tally. What I would say is qualification of our simulation. Okay. So we've got these 3 levels of testing based on that threat analysis and the types of tests we need to do. And also what Warwick are doing is considering dynamic risk considerations, because if you just try to look at a risk at a time, what you miss is how those risks impact each other. So the fact that a particular risk or a particular event in the real world can make another risk become significantly more either higher probability or bigger impact. So they're also trying to look at dynamic risk considerations as well as just a static analysis of the risks. And this is what this diagram is trying to convey, that you can actually, you can't just do a static analysis, it has to be dynamic analysis. Then Nexor, the other partner on the security side, and they're looking at it from a cloud security perspective. And this is a scenario. Hopefully you can see the person. I thought there's no little highlighter pen. Hopefully you can see the person down at the bottom. Now they're on their handset dialing up their pod, which goes into the cloud and eventually makes its way down to through the to the car itself and into the software on the car. And so they're looking at security, the security risks in this system. For example, this is the fleet management system, and their issue here is that assumed cloud is compromised. What's the impact here? So if somebody compromises that cloud communication, what's the impact on security on the ground? And again, they look at this threat model and protect it, and they do a risk assessment. Okay, but this diagram is probably the better one to look at. What happens if the car receives incorrect information? And here's a scenario here, for example, that it's sent a spoof stop command, so somebody spoofs a stop signal to the car, and what's the potential impact on the safety if that risk is realised. Okay, so both Nexor and Warwick contribute to the security side of things, and then we move into the simulation. So at the moment, so far, what we've identified is the things we want to test. Loughborough have told us what the safety threats are. Warwick and Nexor have told us what the security threats are. So they're the things we want to test. Now we've got a simulator which allows us to test this through simulation, and our partner on that is AESIN. And they've got an existing simulator here, which is already in use worldwide, and it allows to model interactions between vehicles and pedestrians with calibrated and validated vehicle behavioural algorithms. So these simulations are intended to be realistic of the real world. And there's, all important, there's an API in there which allows the test bench to communicate with it. And then the way it works is that there's a series of timestamps. You get the positions of all the actors which are nearby to the pod that's under simulation, or the ego vehicle that's being simulated here. So the pod under simulation gets all the information about its nearby actors and can make a decision based on that. So we're mimicking in simulation the types of information that the pod would be getting from its environment via its sensors. In parallel, in that time step, the simulator evaluates what those other actors are doing, because they've all got certain behaviours that have been programmed, and then it all comes together because the simulator updates all its actors. It gets the information back from the simulator, from the pod itself, to say, under these circumstances, this is the decision I've taken, and we move on to the next timestamp. Okay, so we iterate around that loop where all the actors are being updated based on behaviours programmed into them, and the pod software is reacting and telling us what it wants to do based on the reports it's getting about nearby actors. Okay. And from that, we can build a number of experiments and scenarios. So we may modify the map with different trees and buildings. Again, that depends on the information from Loughborough that tells us what the most dangerous scenarios to model. We can modify parked cars, traffic management and works, and all the different actors, how many vehicles are present, the relative positions, their behaviours, their speeds, etc., etc. So that allows us then to model all this within our scenario. And we communicate with that through an API. Here's quite a detailed picture of what the test bench looks like. But what I'll do is I'll go through the text on the left-hand side. What we're doing is taking, if you can see the left-hand side there, the yellow and the blue that feed in those scenarios on safety and security. That allows us then to define a scenario, build a scenario which we can pass to the simulator and say, this is the scenario we're going to be simulating. Then we use constrained random solutions to randomize the behaviors of those actors and the types of cars that are in that scenario. So given a scenario, we can maybe move a few trees around, we can move a few cars around, maybe we got cars going faster or slower, more people, more cyclists, less cyclists. So within the envelope of that safety scenario, we've got various things we can vary, and we use constrained random to vary those. So we can build up a huge number of slightly different scenarios based on constrained random generation, which gets fed into that simulator as the starting scenario. Okay. Also, during the simulation itself, we may want to change the way traffic lights change. We may want to stop so a pedestrian may want to stop them. We may want to decide a pedestrian can cross the road unexpectedly, etc., etc. So during the simulation as well, we can slightly change the behaviour of actors in different ways we want to. So through that simulation, we can hit a very large range of scenarios and try to hit corner cases. The corner cases which we know that the Loughborough have told us, also the corner cases in the security risk analysis as well. Those tests are very, very repeatable, so that if we decide the pod has made a bad decision, then we can repeat that test and say, well, this is what happened. Can you try to debug this particular scenario to the pod manufacturer? And we have high levels of control as well over that testing environment. So instead we're using constrained random stimulus, and we're communicating with the simulator and the software through well-defined APIs. And the couple of important things which we do in this environment, this constrained random, we've been using hardware verification for a long time. T&VS has been doing hardware verification based on constrained random for about 10 years. We've got about 350 engineers who focus on constrained random simulation for hardware verification. What we do is we have coverage of corner cases, and we're able to tell through probing various signals within the environment, within the software, whether we've hit a particular corner case. So although we're doing constrained random, we're probing constantly to make sure we hit the particular corner cases which we're interested in. And because it's constrained random, you haven't got a predefined pass-fail, which you might have in a directed test case. So what we have to do is codify the assertions to make sure, and those assertions typically codify up, don't do anything dangerous, make sure you're always safe. And so throughout the simulation, we can make sure that we don't necessarily know exactly what the pod should do, but what we can do is detect when it's done something unsafe or unexpected. Okay. And then we use the real-world trials to check the fidelity of our simulation. This is the status. I won't go through the status. There's a lot of detail. I won't go through the to-do in a lot of detail as well. I've only got 10 seconds left. So what I'll do is I'll put up the contributors just to say who's working on this. And they all contributed to this paper. And I think I've just finished on time. Thank you.